Today we will be talking about solving optimization problems. The first optimization question we have is a farmer has 150 meters of fencing with which to enclose two adjacent rectangular parts of an animal pen. Assuming all the fencing is used, what are the dimensions of the pen if the area enclosed is to be as large as possible? The first step in solving an optimization question is drawing a sketch or a visual of what the question is asking for. Here we will draw an animal pen and label the width as X and the length as Y. Next, look at what the question is asking for. It is asking for the dimensions that will give the largest possible area, which means we need to maximize the area and look for the maximum dimensions. The next step is formulating the equations that we will use to optimize the question. Normally, you would need to make two equations, one using what information you are given, and the second is what you are looking to find or solve. In this case, we are given 150 meters of fencing, which is parameter, and we are looking to find area. So our equations would be area is equal to x times y, and p will equal to 2x plus 3y. Since the parameter is equal to 150 meters, our equation becomes 150 is equal to 2x plus 3y. The next step is to isolate a variable and sub it into the area equation. We chose to isolate for y, so we have y is equal to 50 minus 2x divided by 3. Next, we sub it into the area equation, which now becomes a of x is equal to 50x minus 2x squared divided by 3. Now that we have our area equation, we want to optimize it to find the maximum, which will occur at a critical point where the derivative is equal to 0. So let's find the derivative first. So a prime of x is equal to 50 minus 4x divided by 3. Now set that equal to 0 and solve for x. We get that x is equal to 37.5 meters. Now before we find the other dimension, we have to double-check using the second derivative test if our work is actually correct and that we actually achieve a maximum. To do so, we find the second derivative, which is a constant of negative 4 over 3. Now if the second derivative test results in a positive solution, then we have a minimum because the function will be concave down. If it results in a negative solution, then we will have a maximum because the function will be concave up. So our second derivative test was a success. The next step is TP find the other dimension, y. Since we already isolated for y, we will use y is equal to 50 minus 2x divided by 3, in which we get that y is equal to 25 meters. Since the question only asked for dimensions and not the area, the last step will be writing a therefore statement that states that the dimensions that will result in the largest area possible is 37.5 meters by 25 meters. The next optimization problem says a flyer is to have an area of 384 centimeters squared with 4 centimeters margins at the bottom and sides and a 6 centimeters margin at the top. What dimensions will give the largest printed area? As usual, the first step is draw a visual of what we have and what we need to find. So we will draw the flyer with the margins and print area inside. The question is asking for the largest printed area, which means we have to find the maxima. The next step is to make the two equations, one using what is given to us and the other is for what we need to find. So we have the area of the flyer, which is 384 centimeters squared, and what we need to find is the area of the printed space within the margins. To do so, the printed area will have an exam of x minus 8 times y minus 10. All we did was subtract the margins from x and y to give us the printed area equation. Now that we have the equations we need, we will isolate for y. So we get y is equal to 384 divided by x. Now we sub 384 divided by x for y into the other equation, which becomes a of x is equal to x minus 8 times 384 divided by x minus 10. Now we expand to get 384 minus 10x plus 80 minus 3072 divided by x. Simplify to get 464 minus 10x minus 3072 times x to the power of negative 1. The next step is finding the derivative, which is a prime of x is equal to minus 10 plus 3072 divided by x squared. Now to find our critical number where the maximum occurs, we make this equal to 0 and solve for x, where we get that x is equal to 17.53 centimeters. Now let's double check our work by doing the second derivative test. So our second derivative is minus 6,144 divided by x cubed. When we sub in 17.53, our answer will be negative, and when the second derivative test is negative, it means the function at that point is concave down and a maximum occurs, so our answers are correct. We still have to find the other dimension y. So we use y is equal to 384 divided by x and sub 17.53 into x to find y, and we get that y is 21.91 centimeters. The last step is writing a therefore statement which states that the maximum print area will have the dimensions of 21.91 centimeters by 17.53 centimeters. The next optimization question is a rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of its base is twice the width. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Find the cost of materials for the cheapest such container. As usual, we always start by a visual sketch to make it easier for us to see what we are working with and what we are looking for. So here we draw a rectangular storage container, and we label the length, width, height. The question is asking for the cost of materials that will be the cheapest to make this container, which means we have to optimize this question to find the minimum cost. The next step is to formulate the equations that we will work with. So in this case, we are given the volume, and we are asked for the cost, so our two equations will be volume and cost. Our volume is equal to 10 meters cubed, so 10 is equal to length times width times height. Now in the question it is given that the length is equal to twice the width, so we can substitute 2w for L, and we get 10 is equal to 2w squared times h. Now we isolate for h so we can use it in our next equation, and we get that h is equal to 5 divided by w squared. Now we have to do the cost function. This one is a little trickier as you first have to find out how much area you have for each side before multiplying it by the cost given in the question. The cost function will equal to the cost of base area plus the cost of the sides. So we only have one base and its cost is $10. We multiply it by the dimensions of the base, which is length times width. Next we add the sides, so the sides cost $6, and we have two sides that are length times height and two sides that are width times height as you can see in the picture. So the cost of the sides will be 6 times 2 times length times height plus 2 times width times height. Now to simplify, we sub in 2w for length, and we get 20w squared plus 6 times width times height. We already have h isolated, so we sub h in so we can make the cost function a function of w, and we get 20w squared plus 36w times 5 divided by w squared. The final cost function after simplification will be c of w is equal to 20w squared plus 180 divided by w. Now that we have the cost function that we need to optimize the minimum cost, we find the first derivative, which is 40w minus 180 divided by w squared. Now set the first derivative equation equal to 0 to get the critical point where the minimum cost should occur and solve for w. We get that w is equal to approximately 1.65 meters. Now we have the width that should give us the cheapest cost, so we use it to find the length and the height of the container that will give the cheapest cost. Since length is 2w, we get that the length is approximately 3.3 meters, and the height is approximately 1.84 meters. Now let's use the second derivative test to actually confirm that these dimensions will give the minimum. So the second derivative is 40 plus 360 divided by w cubed. When we sub in 1.65 for w, we get a positive number. This means that the function is concave up at that value, meaning that a minimum occurs at that value. Now that we have confirmed using the second derivative test, we have all our correct dimensions. However, the questions asks for the cheapest cost, not cheapest dimensions that give the cheapest cost. So we will sub in our dimensions into the original cost function before differentiating it to find the cheapest cost. We will use the most simplified one and sub in 1.65 into the equation. You can also use the one that includes the length and height, but they will all give you the same answer, so use the one in the simplest form unless asked otherwise. We get that the cheapest cost possible is approximately $163.54. The last step is writing a therefore statement that states that the total cost of the materials for the cheapest container is $163.54.